Thank you very much. Welcome this morning. My name is Becky Larson. I am from the Biological Systems Engineering Department, and I'm here to talk a little bit about biochar today. So I've been working on biochar for a while, working in it in a variety of different aspects. So I'm not going to talk about just one thing. I'm going to kind of move around here a little bit, and then hopefully have some time for some questions if you have them. So what is biochar? First, I'm just going to say it's something where a feedstock, some kind of organic feedstock, goes through pyrolysis, and then, traditionally this was started as something where we were trying to produce a bio-oil, a syngas, something you could use for some kind of an energy system, and then the remainder of that was the biochar, right? So if you think of really burning anything, this is combustion in a different way without any oxygen. But anytime you go through a combustion process, there's some kind of ash or char that's remaining. And that's the product that we're going to talk about today. It's really interesting that now maybe sometimes some of us are more focused on the biochar than the bio-oil or the syngas altogether. The biochar is really interesting because it has a lot of different properties, I would say, that we're really still investigating and trying to figure out. I'm sure you've seen a lot of material about biochar recently. It's been very hot, especially in academic circles. I would say every day I could read new articles and to try to keep up with all the information. So I'm going to present to you what I know, but I'm sure lots of others have picked up other information, as this is an area that's transforming pretty quickly. One of the reasons biochar is so interesting is because it has this really interesting structure, right? So it has a lot of surface area. It has a lot of cation exchange capacity. And really the important thing about all of that, and chemistry is definitely not my favorite area, but the important thing about that is if you have all this surface area with all these interesting features on it, it has the potential to bind a lot of things on the biochar, right? So it has a lot of ways that we can transform. So we can have different things in manure, in particular for this talk, attaching to the different areas. And we can kind of modify these biochars we found to change what that surface structure looks like, right? And so then we can try to pinpoint certain things that we want the biochar to do, and what people might be calling sometimes designer chars, and trying to achieve specific things. But we're still kind of in the infancy of that, I would say. And so we're just kind of finding our way through. And all the biochars are different, right? You use different feedstocks. The pyrolysis conditions are different. And so we end up with a lot of different characteristics. So what I want you to take away, if you forget anything that I say in this entire thing, is that biochar really varies in its characteristics and then how it performs in the system you're going to put it in, right? So you can't take generalities of what someone might say of a biochar produced from a hardwood and say that's going to be the same thing as a biochar produced from a corn cob, right? So the feedstocks really change the characteristics of the biochar produced. The pyrolysis production conditions, right? The temperature can range very differently, right? So a biochar produced at maybe 350 degrees Celsius compared to one produced at 750, even with the same feedstock, is also going to be very different. And then you can change the time for which it's within the pyrolysis system. So I can put it at 400 degrees for 2 hours. I can put it at 400 degrees for 24 hours, right? And again, that has very big impacts to what we see. Now, to make that even a little more complicated, we can do a lot of modifications before the pyrolysis occurs, during, and even after, to try to really change what the biochar characteristics are, right? And so you might hear, maybe you've heard about activated carbon, right? That activation is something I'm talking about here, right? So you're doing something, maybe you're adding some kind of cations before you make it, or you're doing some oxidation afterwards, or you're doing some steam treatment, right? All of these things might change the characteristics of the biochar. So as you are interested in biochar and you're working through the things, the most important thing to remember is that the characteristics of it are important. And one biochar performing a certain way that was produced at some conditions may have a very different impact than other ones, right? So for example, this biochar I made out of hardwood might have a huge impact on how nitrogen cycles. Another one I made from some other feedstock might have very little impact to that same type of nitrogen cycling that the other one did. So you have to be very careful in the biochar you're selecting to achieve the goals that you want. Okay, making this move slow. Okay, there we go. So here is a picture. I just want to give you an idea of how different the biochar can be, right? So here's a few pictures. The Journal of Nutrient Management sponsored this lovely talk, this session. And I actually was working on an article for them recently, and we put these pictures within there, right? And so you can see that number A, obviously you could probably guess that that's made of corn cobs. B is made from manure solids, so actually separating dairy manure solids and then pyrolyzing those. C is made from a poplar wood, and D is from birch. So we look at a variety of different feedstocks, and then we might look at running them at different temperatures and then characterizing them and using them in different ways. It's important to note, if you can kind of see these biochars are really low density. So if you can imagine, it might be 5 to 20 pounds for a big cubic foot bag of these things, right? So they're really light. It's really important to think about that, because I think some people think about using them. You have to be careful in how you might integrate them, maybe into a soil system, because they're so light that you might be concerned, particularly like look at how small the particles of that biochar that's made from manure solids are, and that they could be easily blown around, right? And so also when you're looking at people who are saying you have to add a certain amount of weight to a system to achieve some kind of output, you need a lot of biochar if you're talking in weight to hit those applications. So that temperature I was talking about, some of the things that we notice or that researchers have been publishing is that when you increase the temperature, the pH of the biochar that's produced might go up. In the CEC, or the cation exchange capacity, seems to go down, right? So these things are important. As you can think, the pH might, if you're putting it in a soil system, that might be important. If I'm putting it in a processing system where the microbial community needs a certain kind of pH, right? So that might alter some of those things. The cation exchange capacity really talks about how much of a certain type of thing can be absorbed to it, right? So it's really important. There are some tendencies that we're starting to notice here. So we can start to use some of that information to guide us and how we might want to make the chars, and then how we might want to use them. And it goes on, right? So you can see here, different feedstocks lead to different cation exchange capacities. Again, that temperature, you can see that's pretty consistent. We're starting to see some consistency, and that the temperature, as it increases of pyrolysis, you get a decreasing cation exchange capacity. But in the feedstocks, we're kind of all over the board, right? So it's really, you really have to run a lot of tests, and we're trying to figure out, can we run series of tests so that we can reduce all these factors and start to figure out some things to have a little more consistency in understanding what's happening. Okay, so why am I working on biochar? Well, for me, I am interested in applying biochar into manure systems, or maybe other agricultural byproduct systems. So a few of those I'm going to talk about today are going to be about manure storage covers. So we found that you could introduce biochar to a manure system as a manure storage cover to reduce emissions. One of the other things is we can look at increasing nitrogen management. So we found that biochar really, a lot of the chars we've been looking at really impact nitrogen. And we started looking at why that was happening and trying to understand the nitrogen cycling as you start to introduce biochar. And I'll talk a little bit about what we're starting to notice about how it's impacting nitrogen, so that you might think about, as these products become more available, how you might be able to integrate them into your own systems, or how they might be integrated into other systems you're working on. I also think that there's a lot of value with possibly integrating the systems into manure processing systems. So we've looked a lot at integrating biochar into anaerobic digesters. So adding them directly into the manure going into the digester in attempts to maybe increase the biogas production and also to decrease the hydrogen sulfide production. Also, I'm just going to touch a little bit about, I just wanted to note on composting, there's a ton of work going on around biochar and composting. A lot of things that they're starting to notice. I'm going to touch on a few of those just so that people are aware of what's happening there, even though I would say, again, that's a very developing area. And then also I want to talk about why we might look at manure solids and converting those into biochar. And then at the very end, I'm just going to touch on, maybe one of the biggest things that people have talked about is adding biochar just into your land application. And adding them to maybe increase your soil health or to improve crop yields. And again, there's a lot of variability in how you would apply those and how that would work. But I would say almost all of these systems are going to end up with the biochar being land applied when we're talking about manure systems. And then there's some things to think about what is important there. Okay, so I'm going to start with manure storages. We all know that manure storages have a great benefit to us in that they can allow us a lot of management flexibility, right? So especially in places where we have colder climates, where we're trying to avoid certain times of application, or anywhere where you might even have any precipitation, right? It allows us to apply manure at times that are more convenient in terms of the weather, in terms of our operational issues, so a lot of things. So they have a lot of benefits. One of the problems with them, though, is when we look at systems as a whole, manure storages lead to a lot of emission losses, right? And so we lose a lot of methane from there. You can see kind of in this picture, we've been trying in some of these fact sheets and other information to try to outline where some methane emissions might be coming from, right? Because that's a greenhouse gas. We want to try to reduce those emissions. We know enteric emissions are a big one, but we know manure storage is probably number 2 for those farms that incorporate it into their systems. And I think manure storages are really important for that other management thing that I think is more important than the emission losses, but we want to try to mitigate that secondary effect of the emission losses. And so using covers or other things we know can reduce that. And in the same kind of idea, if you think of nitrogen, we lose a lot of nitrogen in manure storage systems too, depending upon the way it's set up. So you can see there, it might range from 3 to 28% of your nitrogen. Now, if you're losing 28% of your nitrogen during storage, now you're going to have to replace that with other nitrogen, right? So there's a lot of reasons we might want to reduce manure storage emissions, environmental, operational, economic, right? There's a lot of reasons we might want to do that. And one of the things we found is that covers are capable of doing that, right? Even just having a crust form on the top of your manure storage can improve some of these. And then going all the way to something like trying to integrate some kind of synthetic cover to capture, and then if you can flare or even use to make energy, right? So these systems are available, but we wanted to see if we could look at biochar as the potential as a manure cover. And so what we did is we took a lot of, a raw wood, and then we steamed it, and we also made it into biochar so that we could look at, well, we want to make sure, should we go through, if this can serve as a cover, do we really want to go through all the process of making biochar? Or are some of the more base forms of that particular feedstock better serving? And then we also said, well, let's try some other biochar. So we made some out of corn cob, right? Because the cheaper you can find a feedstock, the lower cost the biochar might happen to be, right? So we did a bunch of studies, a bunch of buckets and barrels and other lovely manure studies that smelled really great. And we covered them with different things. Sometimes we mixed them in. So you can see on that very bottom right-hand corner, that's when we just kind of applied it as a thick cover. And then sometimes we actually mix the biochar into the manure. We're still really learning about all the impacts of biochar, right? So it's possible that the biochar can serve as just binding all of the possible nitrogen that might be being lost. We thought it could also serve as a cover to keep things just physically from leaving, but we also wanted to incorporate it because what we're also finding is that it really changes the microbial structure of all the microorganisms that might be present. And those microorganisms, in terms of like methane, are really responsible for some of the emission losses. So are we seeing an impact to those? So what we found in this case was the biochars, as you can see, really reduced. I'm going to talk about the ammonia emissions. We saw some reduction in the methane emissions as well, but it was a really noticeable decrease. So if you look at this control, that's just the manure there. And then as you add these other barriers, you can see the biochars performed pretty well in reducing the ammonia emissions. And we were wondering why that might be. So you can see that there's two here. One is the incorporated, that means where we mixed the biochar in, and one is the cover, right? I would say that in the incorporated ones, we ended up, because remember I said that those biochars really are low density. A lot of them did end up moving to the top, but you can also imagine they have a lot of pores in them. So as the manure creeps into there, it can also result in them sinking lower into the thing. So we had more of a cover on the cover ones, but the incorporated ones, I would say, ended up having a significant amount really float to the top as well. But what you'll see is, as we did that, we thought maybe the biochar was uptaking a ton of nitrogen. And we did. We found that as we extracted the nitrogen from the biochar that was on the surface, that it was able to uptake a certain amount of nitrogen within that thing. But what we also found was that in our emissions measurements, what we were able to mitigate was way more than what was able to absorb onto those biochar particles. So in this case, if you're using it as a manure storage cover, it really seems like it functions mostly as a physical barrier. It does uptake some of the nitrogen, but way more of it is just kept from being released from the nitrogen and from the manure, and it's just maintained within the manure profile. So that's important for a few different reasons, right? One, the biochar in this case isn't having so much nitrogen attached that maybe it would have a great fertilizer value. It's also important in that when you're looking at then moving from the storage out to application, if you're able to retain it in the manure, it can be then lost if you're not careful in the way that you apply it, right? So in this case, if you look at this blue chart on the right, Dr. Horacio Aguirre Villegas, who we worked together a lot. He did a lot of modeling of this for me to look at. If you had regular manure, in this case, it was digested, you could see that we lose a lot of emissions in storage and then when we spread. Now, if we put this biochar cover on, it really, really reduces the emission losses during storage. But if we just spread it as surface broadcast, we lose a whole bunch of that, right? And so if we don't also mitigate losses in the application, we're not really gaining a benefit, right? And so if you inject it, or maybe if you incorporate it, those losses go way down. So now you're really seeing some efficiency in terms of your application here. And I also should mention that with the biochar covers, when you go to apply the manure, it can just be incorporated like as you agitate and then sent out with the manure. There's no issues there with that. So that's a simple way to do that. The other thing is, as we modeled it, you can see too that it really draws down the losses of methane during storage and a little bit increases in application afterwards. That's just because you see a lot more N2O. So if we can retain a lot of nitrogen, then you'll get more losses of nitrogen as N2O afterwards. But overall, the effect is an improvement. Okay, so manure storage covers have a potential, I would say right now, in some areas, I've found some places trying to get rid of biochar, but in general, at the moment, the biochar might be a little expensive to use in this kind of system. But I think as we see expansion of this and we see more biochars available, this is a logical place, particularly if you can find a biochar that is available. And in this case, since it is just a physical barrier, the characteristics and the production of the biochar may not be as important in terms of absorption. You just need to be able to have enough structure that it can float on the surface of the manure storage system. Okay, so now I want to move on to talking about integrating biochar into anaerobic digestion processes. So I'm sure a lot of you are familiar with anaerobic digestion. We're taking a lot of feedstocks. In this case, I'm going to talk about manure. The manure has all the microorganisms within it. We put it in a system where there's no oxygen, and then we capture the methane that's produced, right? And that's a great thing because we can use the methane in a variety of ways, and it's a renewable form of energy. The other benefits of that are that it reduces pathogens, it reduces greenhouse gas emissions, so we have a lot of additional environmental benefits to integrating anaerobic digesters. So there's a few problems though, and that one, it would be really nice if our efficiency of methane production could go up. A lot of the carbon is lost as CO2, so the more methane we can produce, the more economically feasible these systems can be. And also hydrogen sulfide is a gas that's produced in that mix. And unfortunately, it has a lot of issues in terms of how we're going to use the gas. And then removing it can be very expensive. So if we can reduce the costs of that, again, we might be able to improve the economic efficiencies. So a lot of people have studied biochar additions to anaerobic digesters, and they're seeing methane increases by 5 to 31%. So again, it depends upon the feedstocks you're adding and the rates of addition. And it's really just quite simple that you take the biochar, as you saw before, whatever you want to make it out of, then you just mix it into the manure as it goes into the digester. The feedstocks can vary significantly, so can the performance. It really also, we were noticing, matters at the particle size you put in the digester. It seems, and we're going to have to keep studying this though, but it seems as the smaller the particle sizes, the more possibly available that carbon. So biochar has a ton of carbon, might be able to be made into methane. But they also saw that it reduces the lag phase. That's the time between when something gets into the digester and then starts producing biogas. So the shorter you can keep something in a digester and produce the methane, the better. And also in some cases, if you have a lot of ammonia, they have found it reduces ammonia inhibition. And it also can decrease inhibition from other things that may attach itself to the biochar. I will say that there are cases where you might not see much methane increase. And so again, the specifics of the biochar is really important. They also, there's been a lot of studies that are now starting to come out where they're combining anaerobic digestion and pyrolysis systems, and they're finding an increase in efficiency and therefore a decrease in costs overall. Even though integrating the two systems may take a little more capital costs, the efficiencies of introducing them together might have a benefit. So the biochar, the thing we've been studying, and I found really interesting when we started running some of these studies, was that we were really able to reduce hydrogen sulfide in biogas. And that wasn't really what we were looking to do. We were actually further kind of with everybody else studying some of these methane improvements and trying to figure out why that was happening. But what we found is that we didn't really get methane improvements when we added the biochar, and there could be a lot of reasons, right? The feedstocks we chose, the temperature we chose to produce it at, the temperature and duration we were running the digester, the amount of addition, the particle size, right? In our case, we didn't see a lot of that carbon in the biochar being converted into methane in this case, which is okay. It didn't hurt the methane production. It just didn't help it so much. But what we did notice when we added some of these biochars is that we had a huge reduction in hydrogen sulfide. And if you can really understand the price tag of removing hydrogen sulfide, even though it's a very small amount that's in the percentage-wise, that's in biogas, it really can be very problematic in terms of its cost, because removing it, even those small things, a lot of people will either add some kind of iron additions into the digester, or they'll use activated carbon after the digester to remove it. And either of those can become quite costly. So we found that it was really interesting. We had this huge, you can see this is way different than any of those other treatments you're seeing there. And the CN is the control, that's the high one. So adding a little bit of the raw wood and the steam treated wood was great. But when we used that same wood and made it into biochar, we had huge reductions in the hydrogen sulfide production. And here's just another way to see that the concentrations were actually knocked down, especially in that first week, which we ran this, to almost 90% reduction under 200 ppm. So we're coming in the control systems at almost 1,000, maybe 900 ppm of hydrogen sulfide, and we're able to reduce that down to maybe like 100. That's pretty significant. So even if you wanted to introduce this into the digester, you might need some secondary to clean it up, but that costly secondary might be much more cost effective. I would say these are preliminary too, right? We're just starting to explore this. And so I think, remember before I said there's a way to do designer chars, as we continue to look at the mechanism by which this happens, we might be able to design a biochar that can even have higher reduction capabilities. And then we would be able to improve this even more. So these are just some of the first results. One of the things we wanted to know after this too was why was this happening, right? So we started looking at some reasons. We initially thought that maybe the sulfate, the actual sulfur that ends up becoming hydrogen sulfide, might be binding to it and to the biochar, and then therefore we can't make hydrogen sulfide. But what we found was that was not the case, right? So that little arrow that says 25 milligrams per liter, that's about how much sulfate is in traditional like dairy manures. I mean, it ranges, but let's say that's there. And so we saw no uptake of sulfate at that with the biochar. So we figured, well, this isn't really what's happening. So we still need some information about, is it impacting the microbial process? Is it maybe inhibiting the sulfur reducing bacteria that lead to the hydrogen sulfide production? Or is it somehow leading to the H2S dissociating, right? And we're binding different things. So we're still trying to explore that. And some of the other things we did was take this same biochar, and instead of putting it in the digester itself, some preliminary results, we tried using it in the post-production. So pushing the gas with a lot of hydrogen sulfide within there, and then seeing if the hydrogen sulfide could be removed in post-production, which is how a lot of the treatment systems work with like activated carbon or some specialized media. And so you can see this purple is a specialized media that is used to remove hydrogen sulfide. And so we saw a similar reductions in some of these different biochar types. See, and all three of these, the black, the green, and the blue, all on the left-hand side, these are all different types of biochar. So the number indicates the temperature it was made at, and then these other things kind of mean what is the feedstock and how it was changed afterwards. It's not super important for me to get into all those details right now, but just to say some of them were looking very similar to this media. And I would say this media can be very, very expensive. So there really is some potential here for reducing some of the biogas, even post-production hydrogen sulfide. Okay, I just want to mention that composting has also been something where we've seen a lot of people integrating biochar. There's a lot of folks, I believe some at River Falls and some others who are UW River Falls who are looking at some of these things. I'm sure others around the country and around the world. I haven't done a lot with composting and biochar, but I wanted to give you a few of the takeaways that I've been seeing in the literature. Adding the biochar to the composting system can change the microbial community. And it seems as though possibly in a beneficial way, and that you might be able to improve the composting in terms of the duration it takes. There's still a lot of work to be done to really understand exactly what's happening there. But what they've noticed is that when they added biochar to some of the composting mixtures, the degradation of the organic material was better, right? So it improved, they were seeing some percent increases in the degradation of that organic material. And they also found that it can reduce nitrogen losses. I'm guessing we do see, as they're pulling it out of some of the compost, a lot of nitrogen binding to that. So that's some of the mechanisms. But in some of the work that I'll talk about in a minute, I think there is some impact to nitrogen cycling, a pretty big impact in terms of biochar being able to limit, I'm guessing, a little bit of the mineralization is a real big driver, and then some other losses in some other ways. It can reduce greenhouse gas emissions. They've noticed reduced emissions from composting piles where they've added biochar, particularly for N2O, which is really potent. And it can increase the potential to bind contaminants. So if you have any contaminants in your manure or something, then it can remove those as well. They are also seeing in some studies where they added biochar to the compost and then applied it to an area that might have a little bit of drought, that the biochar can improve water holding capacity. They've seen that in just biochar application studies as well. So I think we're seeing that it has a lot of potential to improve some things, and it could really help you to kind of envision where some of these might be really useful. Where was I? Here we go. So the next thing I want to talk about is moving manure solids, separated manure solids, and converting those into biochar. So you might ask, why would you want to do this? It's going to take a lot of energy. You're going to have to separate those manure solids, and then you're going to have to put them through the pyrolysis system. And then what are we going to do with that? Well, one of the things we've been noticing with trying to transport some things around, a lot of those solids can contain, you can try to shift some like phosphorus into them, and then you can really reduce the volume by using pyrolysis, like huge volume reductions. And then that may really significantly decrease transport costs. If you also think about manure has pathogen concerns, right? This pyrolysis is at a super high temperature. It eliminates those concerns completely. It also eliminates odor. So you could imagine the markets that might open up to using these products might increase compared to just the raw manure, right? The downsides is that we lose nitrogen during the pyrolysis process, so it's unfortunate. But the one thing about separated manure solids is they don't have a lot of ammonia in them. They're really mostly organic nitrogen. So you see a little less, you have the losses aren't as extreme as if you were trying to pyrolyze something that had a lot of ammonia within it. And then you can use these. Not only could you just move them and sell them as a product, but we've also been finding that it has some potential as some treatment systems. So that's part of the thing I'm interested in, is now how can we use these maybe then on the liquid component of manure to give them a lot more value. And so one of the things that I just wanted to mention, and this is just a big table, I just don't have any other data or any way other to show this, but when we were looking at some of these systems and when you use the manure solids, Joe Sanford, who is a assistant professor at UW Platteville, we were working together and we found that if you dosed these manure solids with magnesium, which was his idea, which has a lot of cations in it, as you then produce the biochar, that changes the surface area, so then the surface characteristics, so then the phosphorus was really clinging to these. So what we found is you might be able to move some phosphorus, right? You've taken the solids, you've pyrolyzed them, you've got some solids in there. But then you might be able to put the liquid manure on here and have a ton more phosphorus from that liquid stream blob onto that biochar that you've made, right? So it will be really interesting. We are just starting this work, but we were blown away that in our preliminary studies, you would normally run these. You can see this increasing phosphorus concentration. You have this little thing, you have this little beaker, and you put the phosphorus and you put the phosphorus solution in there, and you put the biochar in there, and you try to see how much of it can uptake, right? And so we picked these crazy high concentrations, 2,000 milligrams per liter, because we figure it's not going to uptake all that. And what our numbers here in the final solution was showing us is we could have gone way higher. And so that really, really surprised us, because we've tried a lot of other media to try to uptake phosphorus from some of these liquid streams, and they would never be able to perform this way. So we find that this is really exciting. The other thing that we're working on is, it's great if we can remove these things in pyrolysis and that we can maybe attach them, but we really need to know what the fertilizer value is. So we're currently running some mineralization studies to understand how slow release, when these are they released at all as you apply these chars to the thing. So I wish I had that data for you now, but unfortunately, we're still running through so many samples, but we're getting there, and we'll be able to share shortly how well some of these biochars that are made from manure solids are releasing some of the nutrients later. Okay, one of the last topics I want to talk about is using biochar as a management for nitrogen. So a few years back, I think in 2015, I say a few, it seems like yesterday, but so about 6, 7, it probably started the research maybe 8 or 9 years ago. We were looking at putting biochar, and we really were trying to reduce phosphorus runoff. But it turns out we hadn't stumbled across the idea that you need to add those cations, right? The thing I was just explaining to bind phosphorus. So we found it didn't really bind any phosphorus at all in the first studies we were doing. But we did find that as you add biochar into the soil structure, we were seeing huge improvements in nitrate leaching. And so we were curious why that happened, right? So we did these studies and we found total nitrogen. So if you see on these columns, 0 biochar means it's just soil. 1 biochar means it's added by 1% weight, 2%, 5%. The more biochar we added, the less leaching losses we got of nitrogen. And that's really great because if you think about having biochar, it's really wonderful if we could maintain that nitrogen within the soil structure so that either the plants could use it, but in the least, we're not losing it to the groundwater, right? So we started looking a little further into this, and I will say it has been 8 years of going around in circles, but I feel like we're finally starting to really understand some of the things that are happening here. And what we're seeing is a lot of studies are finding nitrogen leaching reduction when you add biochar. And when people previously, before some of the recent work we did, were finding a lot of the biochar, the form that was binding to it was nitrates, right? So nitrates were binding to the biochar in the soil. And so we thought maybe that's it, right? And people were thinking, why is this happening? You know, maybe that's from oxidation from the weathering as the biochar is within the soil, or you're getting these organo-mineral complexes. That's just really saying these organic compounds are sticking to the biochar and then the nitrogen are sticking to those, or what I feel chemists say is unconventional hydrogen bonding, which I have been told is just what people say when they can't figure out any other reason. But so it could be any of these, right? And so we started digging into that. And one of the things we first wanted to check was, well, if we oxidize a char, that increases that ability, right? The oxidation from weathering. So we're going to force that oxidation, not from weathering, but just forcing it to happen using chemicals. And then we're going to see if what is really responsible for the nitrate uptake. And what we found was, if you oxidized it, you really did find, and we studied so many of these, and this is just a subset of some of the oxidized one, you really didn't get a lot of absorption capacity to these biochars before we oxidized them. So new, freshly produced biochar might not bind a lot of nitrates, but once it sits in the soil and oxidizes, or you force it to oxidize, you do get some nitrate binding to that biochar, right? So that's important, right? Because we can't just use any biochars just right out of the gate. Might not have an impact. It might take some time either to have that oxidation happen naturally or to force it with another process. And so we found that, yes, that some of the principles of what we did to change that, the acid group content using the oxidation process was related to its nitrate absorption capacity, which I don't even know why I put this on here. I'm sure you don't care. We also found, though, that minerals on the biochar seem to be important as well, right? So if you had a lot of cations, right, that had some positive charges, it seemed that likely that it could be attracting some of the nitrate to bind to that. And so then when we started moving water through this, right, so you can see this is a retention time. These are different biochars treated differently, not that important. What we're looking at here is the trends. So you're seeing as the time that increases here, the more removal of nitrate we got. So we were flushing nitrate through these biochars and looking at how they performed after we put them through this oxidation process. And we found that just similar to some other nitrogen removals, you needed more time to get more removal, right? So it wasn't an instant thing. That made us start thinking, well, what is really happening here? And so then we started looking at moving to larger systems. So we said, okay, now we're going to take some of that same biochar we use that we know that can uptake nitrate, and we're going to put it in a soil mixture, and we're going to use it in a agricultural treatment system. So this takes runoff from silage, and then it goes into these systems. And what we did is we collected what ran off the surface, we collected what leached through, and then we looked at what happened here. And again, this was when Joe Samford was a PhD student. So I always think the more data I'm showing was never something I was generally out in the field doing. It was always someone else who was doing some hard work out there. So I want to give them their credit. But as we looked at it, we found, look at all these events. So we had all of these rain events, all of these application events. And what you find is when we had biochar mixed into the system, we had a lot less nitrogen leaching, right? So again, we're here. We still see nitrogen losses are lower in these systems. But what we found was that really the weird changes, so this is the influent, we applied organic nitrogen and a lot of ammonia, but mostly organic. And what we found from the control to the biochar is we did reduce some of that nitrate and nitrate. But really what we reduced most significantly leaching through the system was that organic nitrogen, right? And so then we started looking at, well, the reason we might be seeing so much less nitrate move through the system is not just that biochars combine nitrate, but that they also reduce the amount of organic nitrogen that's being converted then to ammonia, then to nitrate, right? So it's affecting the whole system here. And so we started running some of these mass balances. And what we found in this system was that the soil retained most of the nitrogen. So the leached amount in the control was much more than what we leached in the biochar, right? So we lost 50% of the nitrogen in the control through leaching, but we reduced that quite a bit in the biochar systems. And the difference was that most of that ended up in the soil biochar matrix. And that we also had a huge reduction in what was emitted and calculated as emissions that were lost. So when we did some other experiments, and you will see that really the change in soil nitrogen showed us we were binding a lot more of organic nitrogen. So this is this second 4 bars in, this organic nitrogen plus ammonia. You'll see that this is really where we're seeing the big difference of the resulting change. The soil is retaining organic nitrogen. It's retaining a little bit more with the biochar nitrate, but the majority of it is due to that. So then I know I'm probably going to run out of time, and I maybe already did, but the really thing, we then ran some other control columns to really make sure we understood that. And what we found was the same thing. As we added this, biochar decreased the organic nitrogen losses, right? And what we saw, it was the same thing. So when we really controlled the experiment, we really found that leaching was reduced because we reduced gases emissions and we reduced what was leached. And what the really resulting thing was that we're finding that the organic nitrogen is not being converted as easily into some other forms. So there's more work to know why that might be happening, but it's a really interesting thing. So I just want to end this by saying all of these products then result in biochar application. And I like this one because it's a good way to show it. It really depends upon your biochar, but you'll see, depending upon the biochar rate, sometimes you'll add biochar in your yield. So this is the yield from this study. It increased yields up to 15, the application of 15 tons per hectare, but then it decreased after that, right? And so there's a lot of reasons that could be, but I just want everybody to remember that you have to look at your specific char and the application rate. Usually most of the studies are showing improvement until a certain application rate, and then the yield or impact goes down. And it's from a variety of different reasons. I need a whole other presentation to tell you, but I just want you to be aware of that at the end of that. So remember, all biochars are different. Biochar covers can reduce methane and ammonia emissions. If you add it to a digester, you can see methane production improvements depending upon what you choose. You can also see huge reductions in hydrogen sulfide. It has the potential to improve composting outcomes. If you separate manure solids and then pyrolyze them, it has some benefits there. And that then when you use all of these things and you put them in soil, it looks like it can help you manage nitrogen by reducing nitrogen leaching, reducing emissions of nitrogen, and then also by changing how nitrogen is cycling within the soil. So I hope you have learned something. I hope I didn't get too far into any depth in there and that, but I thank you for your time. I'm going to say these research acknowledgements, all of these folks contributed to all this research that we've been working on over a number of years, many of them who are now running their own research groups. And so I just wanted to say thank you. And so now I will open it. It looks like there's some questions there.
So what kind of rates have you been seeing for biochar added to compost?
All over the board, right? So I would say in the research, people have been adding them by weight percentage in a lot of areas. So it's hard for me always to convert back the other way. I just did the other day and now I wrote them down, but I don't know where I wrote them down. I'm sorry. But if someone emails me, I can tell them if they want. But what I'm seeing is people are adding 1% by weight, 2% by weight. These are pretty common ranges. And so that's quite a bit of biochar. What I'm guessing in reality is going to happen is your availability of biochar is going to govern how much you can put in your systems at this point. As we get into the future and biochar is more available, then I think it'll be a little easier. Then maybe these rates will become important. But at this point, we're seeing percentage points. And so that's why I kind of shifted from land applying to these treatment and processing systems, because the amount of biochar you need is a lot. And the idea that you could just apply it to the land at those rates is pretty, at this point, would be totally, I don't see how it could be cost effective unless you could find some for free, which is possible in some areas. I've seen that happen, but you're not going to be very selective in the biochar you're getting. So I would say, I know that was kind of a lengthy answer, but by weight, maybe 1%, 2%, 3% in those ranges. And I think eventually maybe we'll get to a point where obtaining that compost for your compost systems might be possible. Okay, so the next question, which gases are typically generated during the pyrolysis process? That's a good question. So we're still looking into that. I have a whole list of gases that they know are produced, but some of our questions have been how much ammonia is being lost in those systems. And so we're trying right now to integrate this into our big life cycle assessment modeling. And so we're still trying to figure out, some of them haven't been measured in detail. I'll say that. But there is potential, and it changes with every feedstock. So I don't know off the top of my head specifically. I can't remember. It's a long list of gases. But if you send me an email, I can send you that list. And I would say at this point, I don't know if it varies significantly. Like, there's just not a lot of data on it, particularly for manure solids. So we have been working on a proposal to try to measure that. And so I'm hoping I might have an answer of that at some point.
Yeah, how could manure solids be pyrolyzed on farm?
Interestingly enough, these systems you can buy like modular pyrolysis systems. And there's even some really small systems. We even contract with some in Wisconsin to make us when we need bigger batches. And so it's actually a pretty little system. You can buy really little, maybe more simple systems, particularly if you're not interested so much in the biogas or that gases or the oil that's produced, right? So there are some little systems that you can buy or you can make or build. And I think there's been people around the country who have been doing that. You can also buy commercial systems in a really different scale. So you can buy them really small scales to really large scales with varying cost structures. I even see that Joe might be in here. I don't know. He might be able to tell you a little bit more of the range of costs. I think he was looking that up recently. But we were even looking for the farm, one of the research farms out there that you could get one for, I mean, it's going to take you some capital costs, but it's nothing huge. It's nothing bigger than a solid separator or something like that. We're talking in the same kind of ballpark of, you can get some for tens of thousands, or, I would say more like in the hundreds of thousands of dollars, if I'm remembering correctly, could get you a system like that. So you can purchase them commercially, or I think there's even been some people constructing them.
Great. Well, thank you again, Dr. Larson, and the Journal of Nutrient Management.